Good afternoon, Southminster Scholars. Welcome back. This is our third lecture on the solar system, and we're going to talk about truth, beauty, and heliocentrism. In 1543, Copernicus presented an alternate to the geocentric model that we talked about last week. The heliocentric model is sun-centered. Now we're getting somewhere. Professor Summers will compare the two models to us today, pointing out for our benefit which one is myth and which one is more accurate, and is likely to talk about the disadvantages or deficiencies in each one. So let's listen to Dr. Summers as he explains this part of it.
Philosophers discuss truth and beauty. Scientists discuss hypothesis and theory. But what happens in science when you have two competing hypotheses? Then truth and beauty become part of science. And which is more important? And in science, how would you measure the truth or beauty of a hypothesis? These ideas come into play as we look at the next perspective on the solar system, the heliocentric hypothesis of Copernicus. Heliocentric meaning sun-centered, helio being a root word for sun. You'll notice that I said hypothesis and not fact, because I want to examine it in its historical setting. Although we now know that this is the correct model of the solar system, for about 100 years after it was proposed, it was still just a beautiful hypothesis. Even one of science's greatest minds could not prove its truth. The geocentric model had been successful for more than 1,000 years, and it was based on three geometric variations on circular motion. If we have circular motion like this here, we would have uniform motion around a circle. The eccentric circle was a variation where you viewed uniform circular motion, but from a point off center. Then equant motion went a little bit further, and it not only took the observer off center, but also placed the center of the circular motion off center. Finally, the third construct was the epicycle indeferent, which was circular motion around circular motion. Together, these built up a wonderful model of the solar system where Earth was at the center. In the Middle Ages, however, that science was lost in Europe. The knowledge of the geocentric model was carried on through Arabic astronomers. Not only did they carry it on, they almost revered it. They took Ptolemy's book and they called it Almagesty, which comes down to us as Almagest. They also improved some of Ptolemy's model to try and make it correspond more to reality. There were some problems with Ptolemy's model, in particular because Ptolemy only thought that it was a mathematical model designed to make predictions. For example, if we watch this animation of the moon as it goes through its phases, you can see that while the moon goes through its phases, it gets a little bit bigger and a little bit smaller. In Ptolemy's model, the variation of the moon in distance from the Earth was much, much larger and would have produced a much larger amount of size change for the moon. The Arabic astronomers improved not only the moon model, but also models for the outer planets, because the changes in size were true for them as well. And here's an example of an Arabic model called the Al-Shatir model. And this was a model of the outer planets. And if I put it in motion, you can see it has several epicycle deferents. It's a rather complex model, but it was devised to make it the size changes that actually observed for the outer planets to match the size changes in the models. They tried to improve it to make it correspond more to reality. When the Renaissance came to Europe, the Ptolemaic models were rediscovered. In 1175, there was a Latin translation of the Arabic translation of the Almagest. And in 1515, shortly after the invention of the printing press, was the first printing of the Almagest. The other thing that came down in the Renaissance was the Aristotelian philosophy, that the idea that the heavens were perfect and that sphere and circles were the perfect shape. There's a strong contrast in beliefs here of these two ideas that came down. Ptolemy, believing that things are just a mathematical model, it's just a description of movement in the universe, whereas Aristotle believed it was reality. His model believed that there really were crystalline spheres in the heavens that guided the motions of the sun, the moon, and the planets. Into this, we bring the heliocentric model. It is basically an alternative hypothesis to the geocentric model at this time. Now, if this is the geocentric model, you can see Earth is at the center with Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn orbiting around it. The heliocentric model simply switches the place of Earth and Moon and the Sun. The Sun switches to the center, the Earth and the Moon switch out there. This is the model embraced by Copernicus, and it was presented in his book on the revolution of heavenly spheres that was published in 1543. Incidentally, it was published the same year that he died. There is an apocryphal story that says on his deathbed they brought him a copy of his book and he was able to see his life's grand achievement before he died. We don't really know if that's true. There's a lot else we don't really know that's true because Copernicus did not keep notebooks. We don't know much about what he did. All we really know is that he worked part-time on his heliocentric model for more than 30 years. In the absence of knowing what did happen with Copernicus, filling in the void, there are many myths that have grown up about the heliocentric model. And so instead of studying what we do know, which is kind of scant, let's take a look at all these myths, which are probably almost as large or larger than what we do know. Myth number 1. The heliocentric model is much more accurate than the geocentric model. This is not true, because Copernicus did not use any new mathematical techniques. There were no significant advances in either observations or observing tools, and therefore the heliocentric model provided no greater accuracy in predictions. Myth number 2. The heliocentric model is much simpler than the geocentric model. While I would argue that the heliocentric model is definitely simpler in terms of philosophy, in science it's not really simpler, because Copernicus used the eccentrics and epicycles, the same geometric tools that are in the geocentric model. There were no new mathematical techniques developed for Copernicus's model, so really from a scientific standpoint, it wasn't any simpler. Myth number 3. The center of the universe is the most important place. The idea here is that the critics of the heliocentric model resisted demoting Earth from its place in the center. Well, if you look at the Aristotelian philosophy, it says actually the opposite. Perfection in the universe flows upward. The imperfect flows downward. Instead of the Earth being in a revered place in the center of the universe, the heavens were the revered place, and the Earth was the opposite of that. So the Earth not being at the center, from the Aristotle point of view, would actually be a promotion. Myth number 4. Copernicus delayed publishing his work for fear of reprisal from the Church. This I refer to as sort of the Galileo myth, because Galileo got in trouble with the Church for his heliocentric views, so of course Copernicus had to get in trouble with the Church for his heliocentric views. And that's totally wrong as well, because Cardinal Schönberg and Bishop Giza were two major supporters of Copernicus, and they urged Copernicus to publish. Copernicus even dedicated his book to Pope Paul III, and Pope Paul III accepted the dedication. Myth number 5. Copernicus viewed his system as only a mathematical device, not as a representation of reality. This myth arises because Andreas Osiander inserted an introductory letter. And in that introductory letter, fearing reprisal from the Church, he put forth the idea that this was just a mathematical model, that they shouldn't take it too seriously, and please don't get mad at us for doing this. Bishop Giza found this to be horrible, and he attempted to get the letter removed from the publishing of the book. Myth number 6. astronomers quickly embraced the heliocentric model. Well, this was not true, at least not for about 100 years. The Copernicans were few. There were not many people who were willing to embrace the heliocentric model, simply because it didn't provide any better predictions than the geocentric model. It offered no practical advantages to the astronomers. So by the time of Galileo, there were some Copernicans, folks who believed in the heliocentric model, but not many. And finally, myth number 7. Galileo proved that the heliocentric model was correct. This comes from the fact that Galileo was tried by the Inquisition and got into a lot of trouble for espousing the heliocentric viewpoint. But he did not prove the heliocentric viewpoint. And the reason why he failed illustrates a fundamental physical principle discovered by Galileo himself. So, the heliocentric model, as it would have been studied in the time of Galileo, was viewed as an alternative to the geocentric model. It provided several advantages. If we look at the circles of the heliocentric model, it makes much more sense that the smaller sphere of Earth moves through the universe instead of the much larger sphere of the Sun. And certainly makes a lot more sense than the much larger sphere of the stars orbiting around Earth once per day. The smaller things moving makes much more sense than the larger things moving. It also provides a natural explanation for the bounded elongations of Mercury and Venus. As you can see in this diagram, they are interior planets. They're in between Earth and the Sun. And therefore, they could never appear on the opposite side of Earth from the Sun. They would always appear interior and towards the direction of the Sun, which is exactly what we observe for Mercury and Venus. For the exterior planets, Mars, Jupiter, and Saturn, that would explain why they appear largest and are closest to Earth when they are opposite the Sun. Because when they are near the Sun in the sky, they are far away, and when they are opposite the Sun, when the Sun is on one side and on the other side, they are passing closest to Earth. It also provides a natural explanation for the retrograde motion of these outer planets. In this diagram, the blue dot is meant to represent Earth, and the red dot is meant to represent an outer planet. Take Mars, for example. And as Earth in its inner orbit catches up and passes by the outer planet appears to move forward across the plane of the stars, then backward, and then forward again. But it does not involve any true backward motion. It's just the perspective of an inner planet overtaking the outer planet because it's moving on a faster inner track. The final advantage of the heliocentric model is philosophical, that it's a physical model representing nature and is not meant to be just a mathematical device. Although the philosophical arguments don't carry too much weight in astronomy, if all things are equal, we'd like to have both truth and beauty. Now, everything was not wonderful for the heliocentric model. It also had several problems. If I take this globe and I orbit it, I rotate it, if the Earth is spinning once per day, a point on the equator has to go all the way around and back in 24 hours. To do that, it has to be moving at absolutely absurd speed. You would have to be moving at 1,000 kilometers per hour. That doesn't make much sense. Furthermore, if we take this Earth and put it in orbit around the Sun, well then the entire Earth has to be moving at even more absurd speed. It has to be moving at 100,000 kilometers per hour. Come on. That doesn't make much sense to move Earth that fast through the solar system. Also, if Earth is orbiting the Sun, we should see a parallax effect on the stars. That's illustrated by this diagram, that if the Earth is on the near part of its orbit, the angle to stars would be larger, and when it's on its far part of its orbit, the angle to the stars would be smaller. The stars should appear to pull away and come closer, pull away and come closer as Earth moves around its orbit. This is what we would call a parallax effect, and it's not observed for the stars. Now, there is a simple argument that says, oh, this shouldn't happen. That's just to put the stars immensely far away. But that doesn't make any sense, because then you would have this huge empty space beyond Saturn and before the sphere of the stars. And that was considered absurd in this day. Finally, the most damning argument for the heliocentric model is that the scriptures state in several places that Earth does not move. This doesn't sound like a huge problem to a scientist today, but it was a big problem back then when the church dominated not only the daily life, but also your intellectual career. All of these arguments, both for the heliocentric model and against the heliocentric model, are essentially philosophical. Some of them have a scientific basis, but they are simply the idea of which explanation do you prefer. Do you prefer to have Earth moving at this incredible speed of 100,000 kilometers per hour? Or would you rather have the sun orbiting around? Make your choice. Which is a simpler argument to you? The thing in terms of science is that the predictions are equivalent. So if you were an astronomer at the time, what would you think? Would you take an established working model that's been providing predictions your whole life? Or would you go with a more aesthetic alternative? How would you choose? Enter into this man, Galileo, the first telescopic astronomer. And his observations with the telescope helped disprove the Aristotelian view. The Aristotelian view came under attack just shortly before Galileo. The idea that the heavens were perfect and immutable could demonstrably be shown to be wrong. In 1572, they observed a supernova explosion, the appearance of a new star that then faded away. That showed that the stars do indeed change. Galileo's telescope revealed that the moon had mountains, and it showed that not all bodies in the heavens are perfect spheres. Furthermore, Galileo found the moons of Jupiter orbited around Jupiter, and that showed that not everything orbited around Earth. This break with Aristotle came about and was reflected in a new model of the solar system called the Tychonian model. If this is the heliocentric model, in which everything orbits the sun, the Tychonian model would actually be a compromise. It would take the Earth and make it stationary and have the moon and the sun orbiting around Earth, and then it would take all the other planets, Mercury, Venus, Mars, Jupiter, and Saturn, and have them orbit the sun. It seems like a rather complex idea, but it had quite a lot of support at the time of Galileo. So here's where I come to a point what I call Galileo's dilemma. Galileo found that he could prove Aristotle wrong, but given the science of the early 1600s, could he provide proof of the heliocentric hypothesis? This question came up in 1615 when the Catholic Church reviewed Copernicus's book. Even though Pope Paul III had signed off on the book 60 years earlier, it came up for review because of Galileo's work, and they decreed that the heliocentric model could only be referred to as a hypothesis. Galileo was particularly cautioned not to hold or defend the ideas of heliocentrism. However, there was a loophole. There was an implied challenge that if Galileo could provide irrefutable proof of the heliocentric hypothesis, the matter could be reopened. Galileo couldn't resist, and he took up the challenge of proving the heliocentric model. He presented his arguments in 1630 in his book, Dialogue Concerning the Two Chief World Systems. For this book, he was tried by the Inquisition, forced to abjure, and placed under house arrest for the remainder of his life. What was his crime? Well, his crime was providing a wrong proof of the heliocentric model. His idea was that the Earth's motion produces the advance and recession of the tides. As he put it, the ocean, because of its fluid nature, is the only thing that can indicate the motion of the Earth. If Earth were stationary, the tides could not occur. In order to understand that argument, we first have to go through something called the Galilean transformation. And that's simply the idea that in physics, the sum of two motions is a vector sum. If you have two different motions operating, you can combine them with a vector sum. And to see this, let's take a look at the idea of a train. So suppose you have a train conductor walking down the aisle of a train. If you're sitting in the seat, you see him walk past you, say he's moving at about 2 kilometers per hour. However, if you are outside the train, you see the train moving down the track at, say, 30 kilometers per hour. From your perspective outside the train, you add together the 30 kilometers per hour of the train motion and the 2 kilometers per hour of the conductor walking, and you see his total motion as 32 kilometers per hour. Which one's correct? The answer is that they both are. It just depends upon the frame of reference. Measurements depend upon how you are moving with respect to what you are measuring. Galileo applied this to his argument in the tides. He argued that Earth's rotation and orbit combined to produce the tides. And the argument looks something like this. At the antisolar point, the point farthest from the sun, Earth's rotational motion and Earth's orbital motion combine to produce a faster motion. So far on the opposite side of the sun, you're moving a faster speed. At the subsolar point, the rotational motion is going against the orbital motion, and the two subtract, and you get a slower motion. His argument was that acceleration on the far side and deceleration toward the near side created a sloshing of the ocean that created the tides. Wonderful argument. It's just plain wrong is the problem. Problem with this is that the tides are in effect seen from the reference frame of Earth, while the change in speed in his argument is only seen from the reference frame of the sun. He is using a sun reference frame argument to explain an Earth reference frame effect. Furthermore, the high and low tides that we see on Earth cycle in about 12 hours. We get 2 high tides and 2 low tides every day. In Galileo's argument, you should only get 1 high tide and 1 low tide per day. The tides also are observed to occur relative to the sublunar and antilunar points, the points closest and farthest to where the moon is at the time. What's even more intriguing is that Galileo was aware of the correct argument that the moon produces the tides. In his book, he has the simpleton, Simplicio, make this argument. The moon, wandering through the sky, attracts and draws up toward itself a heap of water, which goes along following it, so that the high sea is always in that part that lies under the moon. That's basically a correct argument. However, the wise man, Sagredo, in Galileo's dialogue, dismisses it as, those ridiculous older opinions. Galileo's proof failed because the shift from geocentric to heliocentric is just a transformation of the heavens. Motion is defined relative to some frame of reference, and the various solar system models are essentially equivalent because they are all just changes of reference frame. To go from geocentric to heliocentric, you're changing from the reference frame of Earth to the reference frame of the sun. If you look at the Tychonian model, that's just a rotational transformation of the heliocentric model, taking the heliocentric model and putting it in a spin about Earth. To see that, let's take a look at this animation of the Tychonian model. When you look at this, it looks somewhat like a heliocentric model. It looks like the sun is at the center. But you'll note that there is a circle going through the sun, and actually the Earth here is at the center, and the Earth is fixed. If I put it in motion, you can see that the sun is orbiting around the Earth. But Mercury, Venus, Mars, Jupiter, and Saturn are orbiting around the sun. This is the Tychonian sort of compromise model. If I speed it up, you can see that you start to get sort of seasick, because it's like a wheel that's out of balance and is wobbling around. You see that same sort of curlicue motion that is produced by the epicycle indeferent in the Ptolemaic model. What we really have here is the sun working on a deferent circle and the planets on 5 epicycles around it. This model was due to Tycho Brahe, and he was one of the greatest pre-telescopic observers. He did his observations in a period from about 1570 to 1600. He developed this model because he saw the beauty of the heliocentric model, and he appreciated the explanations, the natural explanations for the bounded elongations of Mercury and Venus, and for the retrograde motion of Mars, Jupiter, and Saturn. Yet, he could not accept the idea that Earth was in motion. To him, it was still absurd that Earth should be spinning or moving around the sun. In the end, all 3 of the models, the Ptolemaic model, the Tychonian model, and the Copernican model, were scientifically equivalent because they all produced the same observations. Not one of them could predict the motions of the planets any better than any other one. And really, I think Galileo might have known this, because in his own copy of the dialogue, he wrote this quote: "Take note, theologians, that in your desire to make matters of faith out of propositions relating to the fixity of sun and earth, you run the risk of eventually having to condemn as heretics those who would declare the earth to stand still and the sun to change position. Eventually, I say, at such a time as it might be physically or logically proved that the earth moves and the sun stands still." In a note in his own copy, he was sort of admitting that he had not truly proved his case. The mistake that he felt the church had made was in calling the heliocentric model heretical. And it wasn't until 1992 when Pope John Paul II produced a statement admitting that the church had erred in condemning Galileo. The philosophical arguments in favor of the heliocentric hypothesis are strong. They are powerful in that it makes much more sense to have everything orbiting around the sun. But in science, they were not enough. In science, in order to prove the heliocentric hypothesis, you would need better predictions, better motions of the heavens. And this would not come from better arguments as produced by Galileo, but instead would come from better data as produced by Tycho Brahe and then analyzed later by Johannes Kepler. And we'll explore that in much more detail in our next lecture. Until then, have a great day.
I'll take your brain to another dimension.
I'm gonna send into outer space. Find another race. I'm gonna send into outer space. Find another race. I'm gonna send into outer space. Find another race. I'm gonna send into outer space. Find another race. I'm gonna send into outer space. Find another race.
attention.